I do a manual focus, and I focus the camera just on that. So if I don't do a manual focus, it'll constantly go back and forth from me to the board, and it comes out not looking very good. Okay, I have your quizzes from last time. I just put the grades in. Does anyone have an objection to me passing these around so you can get yours out of there? Well, some people don't want other people to see their grades, so, you know. I had a student in my pre-calc class who said, no, I don't want you to pass it around, so I just have to make sure everyone's okay. No one's going to... I don't think everyone's going to be, Tom, I failed the quiz. But, you know. Yes, y'all okay with that? You sure? Okay, then I'm just going to start them out over here. Grab yours, pass the pack around, please. Right. Okay, it's 9 o'clock. Hope you all had a good weekend. No quiz today. We are going to continue what we were doing last time. And what we had last time was we were trying to evaluate some limits. Of some functions, and what we were getting, we've looked at what happens when we get 0 over 0, and what do we do when we see that? We do have to do some algebra or some sort of trick or something, right? We do some algebra or trick to do that. We also saw when you do a limit, sometimes we get something like some fixed number on top over 0. And in that case, what happens? It's either going to be positive infinity, negative infinity, right? One of those, I should say. Let me do it this way so you don't get that. Or negative infinity, or does not exist. All right? And then what about, I don't know if we didn't really talk about this, but what happens if you get 0 over fixed? So the top is headed to 0, but the bottom is headed towards a fixed number, like let's say 5. You'd just be 0. Okay, so there's no work to be done there. This is the scenario where you're doing direct substitution and nothing is wrong. Okay. All right, and then what we stopped at last time was when we got infinity over infinity. In fact, this doesn't matter. It can be positive or negative infinity over positive or negative infinity. That's where we were going to go, right? And that's where we stopped. So this is today. This is the question. How do we deal with that? Okay? All right, so before we begin that, we need to establish a very important property of power functions. And here it is. So it says that this is an important property, that if n is any positive integer, 1, 2, 3, 4, doesn't matter, as long as it's a positive integer, and you're taking the limit as x goes to infinity of 1 over x to the nth power, the limit is 0. And I'm going to change this just a little bit. It actually doesn't have to be 1 up here. This could be, again, just any constant, okay? Doesn't have to be the constant 1. It can be like 5 over x to the n. It would still go to 0. Same thing with this, constant. All right? So this one goes to negative infinity. This one goes to positive infinity. And the whole idea here is that if your numerator is staying at the same number and you're dividing it by x to a power, and that power is positive, then raising a number to a power should make it, does raising a number to a bigger power make it bigger or smaller? I'm trying to trick you here. If x is getting big, right, then squaring it's still big, right? And then cubing it's still big. So if x gets large, raising it to a power is going to make it even larger. But just as a side note, be careful, not every number gets bigger when you raise it to a higher power. For example, if you take the number 1/2, right, and you square it, it becomes 1/4, and that just got smaller, right? So in general, raising a number to a bigger power doesn't make the number bigger unless the number is bigger than 1. Then it will do that. But that's just a side note, okay? All right, so we can graph these. We can graph these different powers. Like this one right here, this is the graph of 1 over x, because right now I have the power as set at 1. So this is the graph 1 over x. And as we go to infinity, right, we go this way. As x goes to infinity, we're looking at the graph getting smaller and smaller and smaller. It's approaching 0, right? Out to the right, the graph gets smaller. And then if we go and we let x head over to negative infinity, that direction, again, it gets smaller and smaller and smaller. This is just a visual verification of the rule I just gave you. Now if we change that power to, let's say, the second power, notice still to the right gets smaller, to the left gets smaller, right? Heading to 0 both directions. And this will work for any positive power. Just pay attention to what's happening out the left side and the right side of all of these functions. Okay? They're always the same. Convinced? Good enough? All right. Now, with that, let's take a look at this example here. 3x squared plus 2x minus 5 minus 4x squared plus 1. What was it? 3x squared? Someone have the notes or no? I already forgot. Plus 2x minus 5? Okay. Good enough. We'll just do that. That's good enough. Okay. Let's take the limit as x goes to infinity here. All right, so the first thing we need to do is we need to establish what happens to the numerator and denominator separately. So we're going to try and do direct substitution, but again, substituting infinity is kind of weird, so we're just thinking about what happens as x gets bigger and bigger and bigger. So if I take x squared, right, that's going to get big and positive, and then multiply by 3, we still have something that's becoming infinitely large, right? And then we're adding to it 2x. 2 times infinity should be huge. So we're adding a huge number to a huge number. Still good. Still getting big. And then plus 5 really doesn't make much of a difference, right? Infinity plus 5 is still huge. So the top is headed towards infinity. And then the denominator, let's be a little careful here. We have a huge number. X is going to positive infinity. So when I square it, it's still positive. It's huge. I multiply by a negative number. That's going to make it big but negative, right? So still infinite but negative. And then you add 7. Do you think adding 7 is going to do much to offset that huge negative number? No. So the bottom is headed towards negative infinity. Make sense? Okay, so we do have one of these forms that I said today was about. It was either positive or negative infinity over positive or negative infinity. And in this scenario, we're just like the 0 over 0. This is bad. We're going to do some algebra. Or we're going to do a trick. All right? And I mentioned last class some of the language that we have here. This right here is the form of the limit that we're getting. Okay? It's the form that we're getting. The form is infinity over negative infinity. All right, so the algebra. What we're going to do for the algebra here is if you have a polynomial divided by a polynomial, which is what we have here, right? The numerator is a polynomial, denominator is a polynomial. You may have done this in 1414, college algebra. We are going to look at this is the standard approach for this. We are going to look at the highest power of the denominator, okay? The highest power, x squared. And what we're going to do is we're going to multiply the top and bottom of this fraction by 1. But the way I choose this 1 is going to be very clever. And I'm going to put it in a different color so you can see where I'm inserting the 1. I'll put it out front in just a second. Let me rewrite everything first. Okay, so the 1 that I'm choosing is based upon the highest power of x that I see here, which was x squared, right? I'm going to multiply this by 1 over x squared, 1 over x squared. So I'm not multiplying by x squared over x squared. I'm multiplying by 1 over x squared over 1 over x squared. And let's just see what the effect of that is, all right? Let's see what the effect of this is. This isn't a very natural, like, first thing you would think of doing, okay? But let's see what happens algebraically. So we must distribute this 1 over x squared through, and then this 1 over x squared through. And when we do that, notice I'm writing the limit, still continuing to write the limit. What happens when I multiply 1 over x squared by 3x squared? 3x squared over x squared, right? 3x squared over x squared. And the x's cancel, and all you're left with is the 3, right? So I have 3 up top here, plus, now what happens when I multiply 1 over x squared times 2x? 2x over x squared. And then one of the x's cancels, and what would you be left with? 2 over x. You get the idea here? Yes, no? Okay, how about when I multiply 5 by 1 over x squared? 5 over x squared. All I'm doing is distributing through. Now, at this point, it may not seem like that was very useful, but just hang tight for a second. Now let's do the same thing on the bottom. When I multiply 1 over x squared times negative 4x squared, what am I left with? Just negative 4, right? The x squareds cancel. And then when I multiply 7 by 1 over x squared, I get plus, well, 7 over x squared, right? Okay, so this should be the same exact expression as what we had before, because I multiplied by 1, right? Anything over itself is 1. So multiplying by 1 changes the look, but it's still the same thing. Now, do y'all see what we gained by doing that, though? What was the important property that I put on the board here right before this note? Limit x goes to either positive or negative infinity, right? Of a constant over x to any power, as long as that power is positive integer, that this thing is 0, right? So do you see what's going to happen now if I take the limit? Okay, first of all, as x goes to infinity, 3 doesn't have an x. So 3 doesn't change. 3 is just going to stay 3. But this is a constant over a positive integer power of x. So that should go to 0, shouldn't it? And then this should go to 0. This should go to 0. So the only thing left is what? 3 over negative 4. So negative 3/4. Because again, after I applied the limit, that's going to go to 0. That's going to go to 0. And that's going to go to 0, all based upon that property. Understand? Any questions? So that's a pretty clever little way to go about it, right? coming in with that 1. Now, I picked the highest power of x in the denominator, right? That's what I chose. Let's just discuss why it is I did that and not the highest power in the numerator. Let's just think about it for a second. If you choose the highest power of x in the denominator, then when you do this first multiplication through here, what are you guaranteed to get here? Say it again? A non-zero. So you're going to get a number, aren't you? A fixed, nice constant. And then the rest of it is going to go to 0. Why is the rest of it going to go to 0? You picked the highest power of x, right? So that means everything else that's out here, even if it has x's, they'll cancel. You'll still have more x's in the denominator than you would in the numerator because it wasn't the highest power, right? This guy was the highest power. So what this does is it guarantees that you are going to have a constant, a non-zero constant in the denominator once you take the limit. And we would not want to get 0 on the bottom, would we? Because then we would have like infinity. It could be infinity, negative infinity, and then it would still be a problem. So that's why we pick the highest power of x in the denominator. And then whatever happens on the numerator doesn't matter to us. Because if it turns out to be 0, that's okay. If the numerator is 0, we're done. 0 over a number, we're done. 0. Okay, hopefully that makes sense. So in college algebra, we did this when we were trying to find horizontal asymptotes. So did anybody in your college algebra class do it like this? How many of you did something like this? No? How many of you were taught, if this is your function, you compare the degrees. So you do degree, degree, and you say if the degrees matched, right, then it's just this number over this number. Okay, do you see why that works now? If they're the same degree, okay, if these are the same degree, then when you do this step, what you come out here with is going to be the same, isn't it? And that first multiplication through is going to guarantee you that number in front of this one and the number in front of this one, and everything else is going to go away. So it's a shortcut in college algebra, but in calculus, well, our functions, as you're going to see, are not going to be as nice as this, so we need to understand the method as opposed to the shortcut. Got it? Okay, let's try a different one. I want to touch on something we did last class, and I said, oh wait, no, let's change that to a plus because I wanted to not confuse you, but let's just take a look at this. I'm going a little bit out of order here, but let's try it. What is the limit as x goes to infinity of x cubed minus 3x to the fourth? Okay, I'm putting it in parentheses just so you know that the x is going to infinity on both of these. You could, no, I mean, it's actually bad notation to leave the parentheses out, but. Okay, you ready? Let's see what's happening. What's the behavior of this? What's the form we're getting? What is the form of this limit? Okay, we're going to have a huge number cubed. That's going to be going to infinity, isn't it? Okay, so we have infinity minus, and then here we have infinity to the fourth power, that's huge, times 3, huge, and then minus, we're subtracting it. So we're subtracting an infinitely large number, right? Okay, so what about infinity minus infinity? Is it 0? I mean, yes. Like, think about this. This number's getting big, right? This number's getting big. Which one's getting bigger faster? This one, because it's fourth power, isn't it? And that should have a pretty big impact on which of these gets bigger faster. So it seems like this term right here is dominating this, right? Does that make sense for me to use that word, dominating? Okay. So it doesn't seem like this should be 0. I mean, you could start on a calculator and start plugging in 1, then 2, then 3, then 4. You're not going to get 0. In fact, it's going to start moving away from 0 as you put in numbers. So you can't say infinity minus infinity is 0. In fact, this form right here is another indeterminate form. We've talked about a few of them, and I'm going to summarize them all later. But we have 0 over 0, we have infinity over infinity, we've got all these different ones. Infinity minus infinity is, again, one of those ones where we cannot just say the answer is this. We have to do something. All right? So for this, I'm going to do something, and I think you'll find this pretty natural once I do it. I'm just going to factor out the GCF, greatest common factor. They both have a factor, they both have 3 factors of x, don't they? So I could factor out x cubed. Now, what I've gained here, okay, what I've gained here is that I now have multiplication as opposed to subtraction. Because if I tell you right now, hey, look, I'm going to take a big number and subtract a big number, you're going to have no idea what the answer is, right? Because subtraction, you don't know. You need to know kind of like how big those numbers were. But if I tell you I have 2 numbers multiplied, you can actually come up with an answer. So let's try it. What happens here? As we have a big number, right here. This is a big number cubed. It's positive infinity. So that's a huge positive number, isn't it? Times, now look at this. 1 take away what? A big number. That's going to be a big negative number, isn't it? Big negative number. So I'm going to be multiplying this by a big negative number. So what do you get? What's a huge positive number times a huge negative number? A huge negative number, right? Positive times negative should be negative. They're both big. This should be big. So the answer is negative infinity, which kind of makes sense. I hope it makes sense, because we said this term was going to dominate, right? This was going to dominate everything. And so it may not seem like there's that much of a difference between x cubed and x to the 4th, but when x is huge, that x to the 4th is very powerful, and it overwhelms the x to the x cubed. Yes? Okay. So we are going to use this in the next example, all right? So I'm going to get back. We're going to do more of these when you have infinity minus infinity, don't worry. But I wanted to do that before I do the next example. So what about this? What if we have limit x goes to infinity of 8x to the 4th minus 100 to the 100th power x squared over 4x to the 5th plus 1. All right, let's see if we can make sense out of this. Am I recording? Yes, okay. The other day, on Fridays, I like to do shoot videos for homework solutions and stuff. I've already done them for this class. I've actually done all the homework solutions for the Cal 1, 2, and 3, like all 3 courses. So I'm actually having to go back and do like pre-Cal and some other ones right now. So on Friday, I did like these videos, and freaking I had my microphone off. But it wasn't my fault. I got interrupted. Some people knocked on the door. I was the only one in this room on a Friday. There's no one on campus, and they come and knock on the door, and I turn my mic off and go talk to them, and I forgot to turn it back on. So I lost like an hour and a half of video. It sucked. All right. What do you think here? What's that headed towards? Large, positive or negative? Positive. So I'm just going to kind of write things out here. We have infinity top left, right? Now 100 to the 100 is a huge, huge number, isn't it? And then infinity squared is a huge number, right? And so this whole piece right here is a huge positive number, isn't it? And then I'm going to subtract it. So I'm going to get infinity minus infinity. Agreed? Then over, and on the bottom, what are we having here? Huge number, plus 1, still huge. So we have this. Now, we already discussed the fact that infinity minus infinity is still something we can't tell what's happening unless we just investigate a little more. So can you tell me by looking at this what this is headed towards, the top? Negative infinity, you mean?
Yes.
What is your logic behind that?
Because the 100 to the 100.
The 100 to the 100 is just so much bigger, and so it's going to dominate that? What do y'all think? I put 100 to the 100 there for a reason, because I wanted you to think exactly that. But is that correct?
The value of x is going to impact that adversely, depending on x. X could easily impact that.
Which of these powers is bigger? Well, obviously the fourth. That fourth power should dominate the x squared, shouldn't it? So is that 100 to the 100 enough to overcome the power x to the 4? Is it? And the answer is no. I don't care what number you put here, okay? You can raise that 100 to the billionth power. You could have made this a billion to the billionth power. I agree with you that if we start plugging numbers in, like x is 1, x is 2, this will be negative for a long time. But eventually, this one will dominate that. I can tell you exactly when it would happen. What about when this number, let me go back to 100 to the 100, because that's too many zeros, okay? Okay. So watch this. I'm gonna try and convince you, okay? Let's take a look at this. What if x, because x is going to infinity, right? What happens when x gets to 100 to the 100? Because that is a number that x will get to, right? If it's going to infinity, then that will be 8 times 100 to the 100, all to the fourth, minus 100 to the 100 times 100 to the 100 squared. Do y'all see that? That's me replacing this x with 100 to the 100 and this one with 100 to the 100, yes? Okay, what happens when you take something to a power to a power? What do you do to these powers? Multiply them, right? X to the n to the m is x to the n times m. So you multiply these. So this is 8 times 100 to the what? 400th power minus, now here, what would this be? This would be 100 to the 200, right? Times 100 to the 100. And now what do you do when you have the same base, different exponents? Yep, when you're multiplying, you do this. You add the exponents, ooh, m. So this would be 100 to the 300. And I believe 100 to the 400 is bigger than 100 to the 300, isn't it? And 8 of them. So they will actually dominate, not right away, but x going to infinity means that you never stop. I mean, x is going to grow without bound. So it's the power that determines what's going to happen up top. So this top piece is going to go to infinity, okay? Positive infinity. And then the denominator is going to go to infinity. We already knew that, right? So that means we need algebra. We need some algebra here. So I'm glad you said that, because we need to, if everyone was just like, yeah, this one's going to win, then we don't get to think through it, and understand it. Now I hope we see why it works. I guess what I'm saying is I'm encouraging you to continue to respond, because I kind of need that to help you, all right? All right, algebra, what do you think? What can we do? Multiply by 1 out front. What's the one we're going to use out front? Because we have infinity over infinity, right? This is what we did last time. We did a 1 out front. So what do you want your 1 to be out front? 1 over x to the 5th. And we're doing x to the 5th because that's the highest power that we see in the denominator. And we will have to distribute that through. Continue to write the limit. I don't take the limit away until I actually run x out to infinity. I mean it's going to stay there the whole time. All right, let's distribute. So what happens when you go here, 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 here? So what's the top left of the fraction? Top left. 8 over x. All right, minus what happens when you multiply this times this one. You're going to get 100 to the 100 on top, and on the bottom, x cubed. Then what about here to here? 4. And that's what we wanted, right? We wanted one of these to be a number on the bottom. So we got a 4 there. And then the last one is just what? Plus 1 over x to the 5th. Now look, if you're having trouble with this step from here to here, then you're having trouble with algebra. And then you just put a star next to that. You come see me in my office and I'll just make sure you can do this algebra. This part from here to here is not calculus. The calculus step is right now when we actually let x go to infinity. So let's let x go to infinity and see what happens. So no more limit, okay? Fixed over x to a positive integer goes to what? 0. So top left goes to 0. Top right? 0? Okay. 0 minus 0 on top. And on the bottom, 4. And so you get 0 on the top over 4, which is 0. This limit goes to 0. So we had a limit before this. Well, not before this. The first one I did in class, which was infinity over infinity. And we got negative 3/4, right? And now we just did a different one and we got 0. So far, the limits I've given you, we've had nice answers, right? Like numbers, like a numeric answer. But do you think it's possible to get, like, to have infinity over infinity turn out to be infinity? Let's do one. Let's do, how about x cubed minus x over, the marker's done, over 5x squared minus 4. All right, what about this? Where's the numerator headed? Positive infinity. Now, technically it's headed to infinity minus infinity, but I think you're already putting the link together that that's a higher power than that one. So this one's going to dominate. Okay, that's what I'm going to do. I'm not going to write down infinity minus infinity. I'm just going to put infinity there. And then on the bottom, where's it headed? Positive infinity, right? That minus 4 has no impact on a huge positive number. Well, I mean, it does, but it's not significant, right? What if I made this like 4 million to the 4 million? It's still going to be infinite on the bottom, right? If it's a constant, I will overcome it eventually, right? Okay. Question?
What if it was like 4 to the infinity?
Well, you can't have 4 to the infinity. You could have 4 raised to the x. You could have like 4 raised to the x, and now x is becoming infinite. You tell me, what do you think? What's your instinct? Which of these would win? 5 times x squared, that's going to get infinite. This one, 4 to the infinity, that should become infinite also. Which one do you think is going to win? The quadratic or the exponential? Which one grew faster in college algebra? The exponential grows faster. This one would actually overwhelm that one. But we're not here yet. We're going to talk about exponential and logarithmic functions. We are going to incorporate them in here. But not yet. So good question. This would definitely change the answer though. Okay, so now we have to do some algebra. So you come in, highest power of x on the bottom. Not on the top, on the bottom. So I'm going to multiply top and bottom by 1 over x squared. Yeah? Okay, limit. x goes to infinity, 1 over x squared over 1 over x squared times, and then over here, x cubed minus x, and then 5x squared minus 4. Distribute, rewrite the limit again, and okay, what are the pieces of this fraction here? Top left is what? What's x cubed over x squared? Just x, okay? Minus x over x squared. So just 1 over x. And then this times this will give us 5. And then minus 4 over x squared. Now, if I take my limit at this point, I know that these two are going to vanish, right? They're going to go to 0. You like that? They're going to vanish. But what's still left? I have infinity over 5. So this is headed towards infinity over 5. What do you think about that? A number that's getting huge divided by 5. 5's not changing. That's going to be infinite. That's going to be infinitely large. So these two guys are going to squash down to nothing, but this numerator is going to continue to grow, and this denominator is not going to grow. It's going to stay at 5. So, 10 over 5, that's 2. 100 over 5, that's 20. 1,000 over 5, that's 200. So this thing starts to explode, right? So the answer to this limit is headed towards infinity. So now we've seen with infinity over infinity, we got negative 3/4, we got 0, we got infinity. We could get negative infinity. Here, let me show you how this problem would have turned out to be negative infinity. If I would have changed this to negative and plus, then the top, in the very beginning, the top would have been headed where? Yeah, negative infinity, right? Because we're plugging in infinity here, cubing it, but then making it negative. So you would have negative infinity on top and positive infinity on the bottom. And when you play this game here, the only difference would be that would be plus and that would be minus. And now what you'll have is negative infinity over 5, and then your answer would be negative infinity. So you could have got negative infinity or positive infinity, just depends on the problem. Or a number like negative 3/4 or 0 or something like that. All right, so far, I hope that the algebra that we've done, this little trick, has not been too crazy. All right, let's try something else. Let's try a problem where our algebra gets a little bit, well, messy, I guess. How about this one? Limit x goes to infinity, 5x plus 3 over square root of x squared plus x plus 1. All right, so in college algebra, when you were studying rational functions and you were trying to find the horizontal asymptotes, what you were actually doing was taking the limit as x went to infinity and negative infinity to try and find those. But they, in college algebra, gave you shortcuts. Like if the powers were the same, you just look at the coefficients, and then you probably were also told that if the power of the top was smaller than the bottom, then it would go to 0, the y-axis. And if the power of the top was bigger than the bottom, then you were told that you don't have any. It's going to go like up or down on the left or right. So you're given like 3 scenarios for rational functions. Does that sound familiar from college algebra? Okay. If not, don't worry about it. The class is already behind us. This is not a rational function. So all those things, you could have done the previous problems that I've done that were rational, you could have done them using college algebra. But you can't do this using college algebra because it's not rational. A rational function is a polynomial divided by a polynomial. This is a polynomial divided by a square root function. So you're no longer in that realm, okay? This is not rational, so all the things that you learn for rational go away. All right, let's try and figure out what's happening though. What's the form that we have? Where's the top headed? Infinity? Okay, and then the bottom. Does anybody have like an instinct of where you think this is going? Do you think that the top's getting bigger faster, the bottom, or you think they're about the same? What do you think? I mean, I don't expect you to be right, okay? But does anyone just feel like, you know, hey, this one's growing faster than this one is, or this one's growing faster than that one, or they're about the same, or?
The top's growing fast.
You think the top's faster because it doesn't have a root, or?
Well, the root isn't the root going to go against the squaring?
Yeah, the root does definitely go against the squaring. So, yeah, I mean, it's kind of like, I don't know right now, right? But where does the bottom go? Where does the bottom go? It's infinity squared is infinity plus 1. That's all infinite, right? Now, what's the square root of infinity? It's not as big as the infinity was, right? But, I mean, it's still going to get big, right? It's just smaller than if it wasn't there. Smaller, when I say smaller, I mean it's getting bigger but not as fast. With the square root here, the bottom is still getting huge, but just not as fast as if the root wasn't there. Was there a question? Yes.
Wouldn't the denominator be a plus minus since it's a root?
Oh, that's a good question. What do y'all think? I thought with roots you had to have plus minus.
Well, one can be extemporaneous, one of the answers can be.
So this brings up a good point, because I remember as a student, you know, they drill into my brain like plus or minus root, whenever root, plus or minus, right? And then it never really made sense until, I don't even know if someone told me, I just finally learned and figured it out. But here's the thing about plus or minus. You will only have a plus or minus on a root if you come in there and algebraically take a square root on both sides of an equation. Okay, so for example, if you have like x squared equals 4, all right? If I'm trying to solve for x, my next step is to initiate a square root on both sides. Since I'm going to initiate the square root, I must include both the positive and negative because I initiated the square root. So my next line would be x is plus or minus 2, right? So I have the plus or minus there because I initiated the root. Now, if somebody just sits here and tells me that x is equal to the root of 2, or root of 4, let's say, okay, if somebody tells me, hey, x is the square root of 4, then my answer is 2. Not plus or minus 2, just 2, because the root was there already. So when a root is presented to us as it is then there is no plus or minus. Understand? And they could have put minus out here. They could have just put a minus here. But if they put plus or minus, both plus or minus, they're actually looking at two different functions. So that's not going to happen. That's a good question. That kind of help a little bit? Yeah? Okay. So we didn't initiate that root, so we don't have to look at the plus or minus. All right, so we said top is infinity, and then did we agree that the bottom is infinity also?
Yeah.
Okay. So we have to do some algebra. What are your thoughts here? Go top and bottom by 1 squared? 1 over x squared? Is that what you meant?
I meant just the 1 squared to get rid of the root, and then just have the top 5x plus 3 squared, and then introduce the 1.
5x plus 3 squared. Oh, you mean almost like square the top and bottom?
Yeah.
Am I interpreting that correctly? If I squared the top, I get 5x plus 3, that quantity squared, and if I squared the bottom, the root would go away.
Yeah.
Which would be pretty clever way to go about it. Here's the problem though, okay, unfortunately, is that if you have two functions like this, right? And I'm trying to find the limit as something goes to something. Who cares about this, okay? But if I have two functions and I look at those functions, I go, man, those are kind of messy to work with. Let me just square the top and bottom. Square the top, square the bottom. Is this the same function? Is that the same as multiplying by 1? Because we know that when we multiply anything by 1, it doesn't change it, right? But does squaring it change it? Absolutely. If you square something, top and bottom, you have changed the actual function. Now, if you have an equation and you square both sides of the equation, that's legal. Because what you're doing on one side, you're doing the other, and then now it does introduce possibility of extraneous solutions. But it's still a legitimate algebraic move. But just going and squaring it out of nowhere just to make the roots go away for you is not okay, unfortunately. So it's a good idea, but it won't work. So we can't just square. Now, let's see if you understand the main purpose in the previous problems of multiplying by that 1, which was, like 1 over x squared or something, right? 1 over x to the 5th. The whole purpose of that was to do what? To be able to what?
Get rid of everything.
On the bottom, to get rid of everything except one of them we wanted to leave there, right? And in this case, the instinct would be, I want to get rid of that x squared, yes? So it makes sense to come through, now don't write this down. It makes sense that you would maybe want to do this, right? Here's the problem with this though, is that you have to have your 1 out here. So if I put 1 over x squared here, how do I get that x squared into the root? Right? You can't just slide into the root, right? So this is going to force us to think about something over here on the side. All right? Just think about roots for a second. If I have the square root of x squared, I think everyone would agree that that's x. Yes? It's actually absolute value of x, but we're going to infinity. We can just leave it like this. Okay. What about this? When you do this, this is the same as x squared times x, right? And then this is the same as square root of x squared times square root of x, splitting it up into 2, which is a legal move with radicals. And then this is just x root x. Yes? Okay, now, most of you probably would just go directly from here to here. Show of hands. How many of you would just go from here to here and y'all are okay with that? It's okay if it's nobody. All right, well, everyone here now knows this would go directly to here. All right? That's how you remove factors from a root. That's how you take things out. But what if we're trying to push things into a root? So what if I started here and I told you to push that x inside? Effectively, what would happen to the x as it goes in? Sorry, as that x goes in, what happens to it? It gets squared on its way in. So it's like when you took this x squared out of the root, right? You took the square root of it. But if you wanted to force that x back into the root, you'd have to square it, reverse it. Understand? Sure, everyone's okay with that? So if I'm going to multiply by something out here, that's going to be a 1, right? I need something right here that when I go in with it, it gets squared, and the result is 1 over x squared. So what should I hit it with out here? How about, well, I'll put 1 over on both of them, and then I'll let you say it again. I'm going to come out here with a 1. It's going to be 1 over something, 1 over something. What is it? 1 over just x. 1 over just x. It's critical that you understand why I'm using x. 1 over x. When this 1 over x goes in the root, what happens to things when you force them into roots? They get squared on the way in. Squared, not square rooted, squared. So when 1 over x goes in the root, it's going to become 1 over x squared. You square the top and bottom. Does that make sense? Now, on the top, does it get squared? No. On the top, I'm just going to distribute, right? Like that. But on the bottom, I'm going to write the next line out. What do I get on top when I distribute that 1 over x through? 5 plus 3 over x, right? On the bottom, I'll take this a little slower. I force the 1 over x in, which squares it. But I still have to distribute it to what's in there. And so do you see, by picking 1 over x, I was able to still kill off the highest power of x down here? Because that next step, what am I going to get on that first multiplication through? 1, right? Limit x goes to infinity. 5 plus 3 over x over square root of what? 1 plus 1 over x plus 1 over x squared. Good. And now you may take the limit. This will vanish, this will vanish, and this will vanish. All of those go to 0 because of that property, right? X to any positive integer power. So you get 5 on top, and you get root 1 on the bottom, which is just 1. So you get 5. So for this problem, the numerator is going to infinity, the denominator is going to infinity, but if you were to go out and just keep going out further and further and further, it would approach 5. So if we graphed it, it would have a horizontal asymptote at 5. What do y'all think?
Pretty cool.
All right. All right, I'm going to do the same problem, but I want to change it. We haven't done this yet. I want to go to negative infinity. Let's see what happens. So I'm changing it to negative infinity there. We have not done negative infinity, so the only difference is that our number's getting big, but it's negative. So let's see if that has any impact on things here. Where's my numerator headed? So 5 times negative infinity, that's a huge negative number, plus 3, still headed towards negative infinity. Understand? Negative infinity squared should be positive infinity, right? Plus negative infinity. So this is almost looking like this. This is infinity plus negative infinity plus 1. Do y'all see that? That's what's happening there? Do y'all see this? And then it's underneath the square root. But what can you tell me about this and this together? Who's going to dominate? This one right here, because it's squared, right? So this is going to dominate. So that looks like it's heading towards infinity plus 1, which is just infinity. So we're getting this. Oh, and then the square root, right? So this is square root. This one beats these two out. So this one's going to dominate. So root infinity is still infinity. We good? Do y'all kind of see what I was saying, like calculus, like in the beginning at least, a lot of number sense, a lot of thinking through like what one thing's getting big and who, you know, it's what I was referring to. All right, now what? Algebra? Same, it's going to be the same thing, 1 over x on the outside. So I'm going to skip through that step and let's just see where we would be. Limit x goes to infinity, negative infinity. It was 5 plus 3 over x over root 1 plus 1 over x plus 1 over x squared. Right? That'll vanish, that'll vanish, that'll vanish, and all you're left with is 5 again, right? So we're getting 5. It won't always be the same thing, all right? Sometimes you can have different limits on different sides. Like left, going out to negative infinity, you could have, you know, maybe negative 5, and on the right, positive 5. Just depends, yes.
So basically that means on the graph that as you approach negative infinity, infinity, they're both going to 5.
Yes. Mm-hmm. Yep. We call that in algebra the left-hand behavior and the right-hand behavior, or asymptotes, horizontal. All right. You good? Feel all right? Where are you? There you you are. Let's do that one. X squared plus 4 underneath the root. I'll pass the sign-in sheet around. Thank you. Okay, what's the form of this limit? So this whole thing right here is infinity, positive infinity, minus infinity, which is not 0, right? That is still something we cannot determine. That's, I mean, right now we have really these three main types of limits that require some algebra or some work, right? Now we also have this one. But with this one, we know it's either infinity, negative infinity, or doesn't exist. And that's where we like use a number line and come in and test and see what happens. But that we can't really determine, but the way we go about that is different than these. In all three of these cases, we have to do something. So I gave you one like this earlier, and didn't I factor? Isn't that the way I convinced you? I did a GCF and I pulled out something and then turned it into multiplication, and it was like, oh, okay. You can see that the highest power of x dominates, right? This one you can't do that because you can't factor anything out, right? Is it x minus 4 minus x?
I mean, x plus 4. X plus
2. Okay, now you got to be careful there. What you're suggesting is that this is equal to this. That's not true. That would, you cannot, when you have a root on a sum or a difference, you cannot do the root of each one individually. I'll give you again, when I was a student of math, there were a lot of things like exactly like that I wasn't sure I could do. And I would do it and I'd make a mistake. And I finally got to the point where it was like, okay, let me just check it to see if it actually works. According to that, that should be equal to this. So, right, I mean, that's basically what you would be doing here, something like that, just taking the root of each one. So root of 9 I know is 3, and root of 16 I know is 4. So the right side of this is 7. Now this is really root 25, and that's 5. Wait a minute, something is not right here. What's not right? Well, you're not allowed to do that. Okay, so you can't split. For the same reason that when you have x plus 2 squared, you cannot just square each one. What do you have to do here? You have to FOIL it out, right? And you always get that middle term. You cannot do the 2 on each one. Here, you cannot do the square root on each one. You can see it even better if you rewrite it using rational exponents, because the root means this, right? And so doing this would mean you're doing the half power on that, and that's like you doing 2 on this and 2. Does that make sense? Okay. So, unfortunately, that's not going to work. Any other ideas before I show you?